Okay, so let me go over that first quiz problem. I think in the first problem we are asked to find the limit, and the limit is x goes to 1, is it? And I think I remember x minus 1 squared in the denominator. And what's the numerator? 2 minus x. Okay, so if you have a ratio, let's see what's happening to the numerator and the denominator. Notice that here's let's say 1, right? And x is going to 1 from either side. And then what would be the limit of the what's the limit of the denominator? As x goes to 1, this one goes to 0. However, what's the sign of the denominator? When x is close to 1, what's the sign? Is it positive or negative? X minus 1 squared, when x is close to 1, is it positive or negative? It's positive because of the square. And what's the limit of this guy? 1, which is also positive. So the ratio is positive when x is close to 1. And the limit of the numerator is non-zero. Limit of the denominator is 0. And when that happens, I said the limit of the ratio is infinity, right? You might say, why that's the case? Well, that's the case because imagine that the numerator is almost like 1 when x is close to 1, and then the denominator is becoming 0, right? So it's becoming like 0.00001, 0.0000001, right? And so when you divide something by such small numbers, the ratio is big, right? So that's why as x gets closer and closer to 1, the value of the ratio will be, not the value, the ratio will tend to infinity. Is that making sense? Think about, this is almost like the same case as just 1 over x squared, right? What happens with 1 over x squared at 0? It goes to infinity. The function blows up to infinity at 0. Okay. Any questions on that? All right. So let me move on to what we want to do now. Last time, did I go over the definition of a horizontal asymptote? And I also told you the definition of a vertical asymptote, I see. Okay, let me just do an example today, and then we are going to move on to a new topic. Let's say I have the following example. What was the example that I wanted to do? Let's say I have the function x squared minus 2x plus 1 divided by x squared plus x minus 2. And let's call this function g of x. And the question is find the horizontal asymptotes and the vertical asymptotes of G. So what are the horizontal asymptotes and what are the vertical asymptotes of this function? Okay, so what are we going to say here? First of all, let's find the horizontal asymptotes. So how do I find the horizontal asymptotes? for a function, I take the limit at infinity and negative infinity, right? So what's the limit as x goes to infinity of the function x squared minus 2x plus 1 over x squared plus x minus 2. This limit, remember I said, if you're looking at the limit as x goes to infinity for a rational function, you can just look at the dominating terms. So what's the dominating term on the numerator? X squared. What's the dominating term in the denominator? Notice that these two functions are not the same, right? These two functions, I'm not saying they are the same. All I'm saying is that they have the same limits at infinity. Okay? So don't think that I'm saying that they are the same functions. So what's the limit now? Well, the limit now is 1. So this already tells me that y equals to 1 is a horizontal asymptote, okay? And I also have to look at the limit as x goes to negative infinity of this same function, x squared, what is that, minus 2x plus 1 over x squared minus plus x minus 2. And this is also infinity as well, right? It's not so infinity, sorry. This is 1 as well, right? And so I'm not getting a different number. If I had a distinct limit here, a different limit here, then I would have another horizontal asymptote. So in this for this function, I have only one horizontal asymptote, so I'm done. How about vertical asymptotes? To find the vertical asymptotes, what do I have to do? I have to figure out the values of x where the function goes to infinity or negative infinity, right? Find the values of x where the function goes to infinity or negative infinity. So at what values of x will a ratio go to infinity or negative infinity? Well, what are the potential values of x where x might be going to infinity or negative infinity? Well, these are the values of x where the denominator would be 0, right? Those are the potential places where the limit will be infinity or negative infinity. So you have to find where the denominator vanishes. Once again, the function we have at hand is this, and I have to figure out where the denominator vanishes. So where does the denominator vanish? I have x squared plus x minus 2, and I can factor that out as what? Is it x minus 1 times x plus 2? And so I see that the denominator vanishes at 1 and at negative 2. So these are the two potential places where the limit could be plus or minus infinity. But notice that in this problem, I am going to have a vertical asymptote at negative 2, but I'm not going to have a vertical asymptote at 1. Okay, just because the denominator vanishes at 1 doesn't mean I have a vertical asymptote there. Why? Because notice that the numerator also vanishes at 1. You realize that? The numerator also vanishes 1. So when that happens, you should factor out the function and factor out the numerator and the denominator. So if I factor out the numerator, I get what? X minus 1 times x minus 1. Here I have x minus 1, x plus 2. Now I can cancel out this x minus 1, and I am left with x minus 1 over x plus 2. So what I'm saying is that g of x is equal to this as long as x is not equal to 1, right? G of x is given by the simpler ratio as long as x is not 1. But when we take the limit at 1, it doesn't matter what's happening exactly at 1. What matters is what's happening near 1. So now notice that if this new ratio that I have, it doesn't vanish at 1 anymore, right? The denominator doesn't vanish at 1 anymore. So I don't have a vertical asymptote at 1. However, the denominator still vanishes at -2, but the numerator doesn't vanish at -2. So the only vertical asymptote that I have here is x equals to -2. That's the only vertical asymptote. Again, having a vertical asymptote at -2 means if you look at the limit at -2 from the right side or the left side, what would be the limit? The limit would be infinity or -infinity. What would be the limit at 1? Can someone tell me what's the limit of this function at 1? What is the limit of this function at 1? If I take the limit of this guy at 1, what's going to happen? You plug in 1, you get 0 over 0. You factor out, you cancel out, and then you plug in 1 now. What happens? The limit is 0. The limit of this function at 1 is 0. It's not infinity, it's not -infinity, right? That's why at 1 you don't have a vertical asymptote. Remember, vertical asymptote means the function blows up at that point, or blows down, that is, goes to infinity or -infinity. However, at -2, what's happening? Let's say you are going to -2 from the right, okay? So then the denominator vanishes, right? However, the numerator doesn't vanish. What's the limit of the numerator as x goes to -2? It's non-zero, right? -3, non-zero. Limit of the denominator is 0. Then the limit of the ratio would be plus or minus infinity. I don't care whether it's plus or minus in this case, because all I want to check is that the limit is one of them, right? Am I making sense? So in this case, we would say that there is only one. This is the only vertical asymptote that I have. Okay, did that make sense? The shortcut to say is that before you decide whether the vertical asymptotes, see if you can factor out the numerator and the denominator, cancel out, reduce the fraction as much as you can, and then decide the vertical asymptotes. Is that okay? All right. We are done with 3.4. Okay. The next thing that I want to do is go to section 1.8, which we won't be able to finish today, but we will be done mostly. This one is on continuous functions. Okay, so we are going to start. We have the following definition. A function f is continuous. So I am going to use CTS to mean continuous. A function f is continuous at a number a, if the following two properties are satisfied. One, f of a is defined. So the function is defined at a, meaning that a is in the domain of the function, right? And 2 is defined, i.e. A is inside the domain of the function. And 2, if I look at the limit as x goes to a of f of x, remember, the limit of a function at a number a is not necessarily the same as the value of f at a, right? Remember, the function may not even be defined at a, still it might have a limit at a, right? A function may not be defined at a, still may have a limit at a. So the second requirement is that the limit of f at a is in fact the same as the value of the function at a. The limit of the function at a is the same as the value of the function at a. So that's what we mean when we say that f is continuous at a number. We are going to use some other terminologies like this. F is discontinuous at a if f is not continuous at a. Surprise. Okay, we are also going to use a couple of other terminologies. F is continuous on an interval I if f is continuous at every number a inside of I. Okay, so f is continuous on the entire interval of numbers if it is continuous at every single point inside that interval. Okay. Let's look at some examples to examine this definition further. Let's take this function f of x, which is given by x squared minus 1 over x minus 1. And let me ask you, is this function continuous at 1? Was that? No, because right away I can say no, because what's the first condition? The first condition is that the function must be defined at 1, which it is not. Right? It's not continuous. So this function is discontinuous at 1. Why again? Because it's undefined at 1. I don't even have to look at the second condition. And how about this function here? So f of x is, let me use another letter here, sorry. Let's use the function g of x to be x squared minus 1 divided by x minus 1 if x is 1. But otherwise the value of the function is 4. So when x is equal to 1, the value of the function is 4. Now the function g is defined at 1, right? The function is defined at 1. Its value at 1 is given by 4, right? Is this function continuous or discontinuous at 1? Is it continuous or discontinuous at 1? Why is it discontinuous? What's the limit of g at 1? What is the limit of g at 1? What's that? Yeah, the limit. So remember this function, if I look at the function x squared minus 1 over x minus 1 is equal to x minus 1 times x plus 1 over x minus 1, and that's equal to x plus 1, right? And so that tells me this equalities hold as long as x is not 1, right? So this tells me that the limit of this function as x goes to 1 is 2, right? Because it's given by the limit of this guy at 1. Okay, so I know that the limit as x goes to 1 of g of x would be the same as the limit as x goes to 1 of x squared minus 1 over x minus 1. Do you agree with that? Why am I not saying that the limit of g of x is equal to the limit of 4? Was that? So why am I saying that when I'm taking the limit of g, I'm only taking the limit of this guy? Why not this guy? Because remember, when we are taking limit, it doesn't, this is the value of the function exactly at 1, right? Again, when I take the limit of the function, I'm not interested in the exact value of the function at 1. I want to know what's happening as x gets closer and closer to 1. So when x is not 1 but close to 1, the value of the function is given by this. Okay? So this limit, as we saw, is the same as the limit as x goes to 1 of the function x plus 1, because we can cancel out, and then the limit becomes 2. And notice that then the limit as x goes to 1 of g of x is not the same as g of 1, right? It's not the same as g of 1. Because what is g of 1? G of 1 in our problem is 4, right? But the limit is 2. So the limit of the function at 1 is 2, but the value of the function at 1 is 4, which are different. Is everybody okay with that? However, is it clear that if I define a new function h of x, which is still x squared minus 1 over x minus 1 when x is not equal to 1 and the value is 2 when x is 1, is it continuous at 1 now? So h is continuous at 1 since h of 1, which is 2, is the same as the limit of the function at 1, right? Again, the limit of h of x is the same as the limit of that ratio, which is 2, and which is the same as h of 1 in this case. Is everybody okay? Let's think about the graphs of these functions and see what's going on. Here's my x-axis. Here's the y-axis. And here is the graph of that line, let's say. And let's say this height is 2 and here is 1. Okay? So this is the graph of which function? If I have a hole there, this is the graph of my my first function. I called it what? F, I think, right? So the graph that I have now, this is the graph of F. What's the graph of G? G is the same thing, except at 1, I said that the value of the function is given by 4. So that's G. Let me use red for that. That's G. And then, so now I have the graph of G. But what would be the graph of H? Notice that what I did with H, all I did is I basically defined the function intentionally to be 2, so that this hole is no more a hole, it's filled in, right? So I'm making this function continuous at 1. Is everybody okay? Now in the first, so for the function f, for the function g, they both were discontinuous at 1, but we call this discontinuity a removable discontinuity. Why? Because I was able to redefine the function at 1, making it continuous at 1. Right? The function f and the function g, both of them were discontinuous at 1, but both of them have removable discontinuities at 1, because I was able to redefine the function just at 1, right? I only changed the function, both functions at 1, and made it continuous by defining h, right? Is everybody okay with that? Okay. So that's one example. Let's look at another example. So let me maybe write it down here. The discontinuity of f and g above at 1 is known as a removable discontinuity. Okay, so let's look at another example. Let's say I have the function, let me use another letter, capital G of x, and it's given by the function x squared if x is larger than 1, and it is given by the function negative x squared if x is less than 1. So that's the function I have. Notice that when x is strictly less than 1, right? When x is strictly less than 1, the value of the function is given by just negative x squared. Now think about the graph of negative x squared, right? On the left side of 1, do I have any hole there? Do I have any problem in the graph? So there is no discontinuity when x is smaller than 1. Same way there will not be any discontinuity when x is larger than 1, because the function is given by x squared, and then look at the graph of x squared there. So the only discontinuity for this function can happen at the breaking point 1. Okay? And so is this function continuous or discontinuous at 1? So is g of x continuous at x equals to 1? How would I answer that? Well, I just have to look at the conditions. So what are the conditions? Number one, it has to be defined at 1, right? Is it defined at 1? G of 1 is defined, isn't it? What is the value of G of 1? Yeah, because in my formula I said when x is equal to 1, you're going to use the first formula, right? And by that I get 1 squared, which is 1. So G of 1 is defined. Now let's check the second condition. What's the limit of the function at 1? So what is the limit as x goes to 1 of g of x? And is this limit equal to g of 1, which is 1, right? So the question would be, is this limit 1? Well, let's see. How can I come up with the limit of g at 1? The problem is, when I take the limit of g at 1, I don't have one single formula for the function. So what do I have to do? I have to look at the limit at 1 from the right and left separately, and then I can use those formulas. So I look at the limit as x goes to 1 from the right of g of x. And what is that limit? Well, when x goes to 1 from the right, it means what? It means x is larger than 1, right? X is on the right side of 1. So that means that when x is larger than 1, the function formula is what? X squared. And what's the limit of x squared as x goes to 1? Well, that's 1. Okay. How about the limit as x goes to 1 from the left of g of x? Well, this time x is smaller than 1 on the left side of 1, which would mean that the function is given by the second formula, which would mean that the limit is -1. And unfortunately, they are different. So what does it tell me about this guy? This guy does not exist, right? The two-sided limit at 1, doesn't exist, right? The limit at 1 doesn't exist, let alone be equal to the value of the function at 1, right? Is that making sense? And when you have a point where the left-hand limit and the right-hand limit are different, then we say that we have a jump discontinuity, okay? And look at how the graph looks like here. So this would be a jump discontinuity. Again, jump discontinuity means at a point you have a jump discontinuity, means the left-hand limit there and the right-hand limit there are different. Okay, so here's how the graph of these two looks like. Okay, so the graph of, we are going to break up at 1. So right here is 1, and I am supposed to get a parabola like this. So this is part of what? This is part of x squared, right? And what do I get for negative x squared? So this is 1 here. So so that's the graph, okay? The graph, this guy is the graph of negative x squared, right? So remember, g is given by x squared when x is bigger than 1. So that's why I took the part of the graph of x squared on the right side of 1, and I took the part of the negative x squared where x is less than 1. So that's the graph of g of x, and I have a jump discontinuity at 1. So here I have jump discontinuity at 1. Again, what happened here? What happened here is that the limit as x goes to 1 from the right of this function is not equal to the limit as x goes to 1 from the left of this function. So the second condition was not satisfied. Okay? Is everybody okay? Now here's my question. Remember in my first example, I had 3 functions. 2 of them were discontinuous at 1. The third one was continuous at 1. And I called that a removable discontinuity because I was able to redefine the value of the function at 1 and made it continuous at 1. Is that possible? My question to you, look at this function. Can I redefine this function at 1? Can I redefine the function at 1 and then make it continuous? Is it possible? Is it possible at all? Well, it's not possible, right? Because if right now, the definition of the value at 1 is what? 1. If you make it negative 1, still it's going to be discontinuous, right? If you make it any value in between, it's going to be still discontinuous, right? The limit at 1 still wouldn't exist, right? Am I making sense? So this is not a removable discontinuity. Okay, another example. Let's take the function f of x to be 1 over x minus 1 squared. Is this function continuous at 1? Is f continuous at 1? Well, this is pretty easy to say, right? This is pretty easy to say, right? No. Why? Yes, it's just undefined because f of 1 is undefined. Okay, that was pretty easy. How about I now say that instead of having this, instead of having f like that, what if I have the function f a little bit different now? I have f of x is still 1 over x minus 1 whole squared when x is not equal to 1, but I define the value of the function to be 0 when x is equal to 1. How's that? Now the function is defined at 1, right? F is defined at 1. Is it now continuous at 1? Is it continuous at 1? Yes, no? Look at the function. So there are 2 conditions for continuity, right? Defined at 1 and the limit at 1 must be equal to the value of the function at 1, right? So the limit of this function at 1 must be equal to 0. If it is continuous at 1, the limit of the function at 1 needs to be 0, right? But what's the limit of this function at 1? What's the limit of this function at 1? It is infinity, isn't it? Because when you take the limit of f, so if you take the limit as x goes to 1 from the right or left, but here, in this case, I could say that this is the same as what? Again, when I'm trying to compute the limit of the function at 1, it doesn't matter. I don't consider the value of the function at exactly 1. So when x is close to 1 but not equal to 1, the value of the function is given by what? 1 over x minus 1 squared. And the limit of that guy, because the numerator has non-zero limit, the denominator has limit 0, then the ratio will have limit plus or minus infinity. In this case it's plus because the ratio is positive when x is close to 1. Okay? So the limit is not even defined as a number, so it cannot be equal to the value of the function at 1. Right? So what's going on here? What do I have at 1? I have a vertical asymptote. Very good. So this is another kind of discontinuity, that you have a vertical asymptote at a point. So let's see if you can remove this discontinuity in any way. So let's say, let me take the line here. So this line that I have here, that's the line at x equals to 1. Okay, well, how is the graph of this function? It's going to look like this. And I hope I can make it nicely. Maybe not that nicely, but good enough. Okay, so at 1, these are supposed to be symmetric, right? They should be mirror images of each other on both sides of 1. But okay, that's my limitation of drawing here. Okay, so what was the value of the function at 1? It's 0. So that's how the graph looks like. Now, is this a removable discontinuity? No, because it doesn't matter how you redefine the function at 1. The limit of the function at 1 is always going to be infinity, and then you cannot remove that discontinuity. Okay, so I have a vertical asymptote at x equals to 1. Okay, is everybody okay with that? Alright, you should be able to start your homework at 1.8, but I'm not done with it. Okay, so you won't be able to do all of them.